Well, I'm going to start it, and I hope you all can hear me clearly. So let's start it. So so today I'm going to go over the midterm 2, give a short review of that. And before I go into detail, let's look at the big picture of what we learned after the midterm 1. So the first thing we learn is the probability distribution. And I have pre-recorded the review, so please look at that. After that, we go over the sampling distribution, and then is the estimation, which is point estimate, as well as the confidence interval. And the last part, we talk about hypothesis testing, which is t-test and z-test. Since the professor says we only covered z-test in our midterm, so I'm not going to talk about t-test. I will leave that to the final one. So for the first part, the probability distribution, you better go and check the link I sent you on the Canvas. It's the same here, showing here. So I'm going to skip that part for the time is limited. So let's go and talk about the sampling distribution. So what is sampling distribution? Please take a second to think about that. So sample distribution, as the name suggests, first of all, is a distribution. It's a distribution that describes the probability, describe the characteristic of the sample. So let's say we have a population here, and then we know the distribution of it, and we plot it here, the red line. And every time we take a sample, for example, sample of size n, which here is showing the n is 5, and then we compute the x bars of this sample. And then we repeat these steps over and over again, repeat many times. So we take many samples from the same population. And then we use all these sample data to build a distribution. So that is the distribution of the sample mean. So actually it's the distribution of the sample mean, and it's called the distribution sample, a sampling distribution. And you can see that the width of the sampling distribution is much narrower than the original population distribution. And one of the important things you would want to know is like, how do we actually characterize, how do we actually calculate it, some parameter of the distribution? So this table is actually very useful. So please look at it very carefully. And on the right-hand side is actually the condition that we can use this sampling distribution. So we also call this condition as a normality condition. So basically, for the categorical type of data, we're going to look at these two conditions. We need to satisfy both. And then for the quantitative data, we are going to look at whether the sample size is greater than 30. If the sample size is less than 30, we're going to check whether it is a normal population. What is a normal population? So these are the formula here. So given a population, and if we know the, for example, for the categorical data, if we know the population proportion, we can use this equation to find the sigma x bar or sigma p hat. So we can use this population proportion to find that. If we don't know this population proportion, if we only know this p hat, the sample proportion, we're going to replace this formula to p hat times 1 minus p hat over n and take the square root of all of that. The same things happen when you look at the quantitative data. If we know the population standard deviation sigma, we can use this. If we don't know, so if sigma is unknown, we are going to use another. We're going to replace the sigma with the sample standard deviation over square root of n. So this is the table, and let's look at some example. So here's an example, one of the quantitative data, and here are the website. It's actually a YouTube video. I screenshot the problem there, and if you want to check it, feel free to go and check it. And there's also a solution there, but I'm also going to talk about it. So this example is saying that a pharmaceutical company that makes pills, they claim the population average is 100 milligrams and the population standard deviation is 1.2 milligrams. So which means mu is 100 and sigma is 1.2. So it says we find the average of 20 samples to be 99.5 milligrams. And how probable is it that we would get an average of 20 pills of less than or equal than 99.5 milligrams? So as the problem says, asking the probability of the average of 20 pills, which is x bar, less than or equal than 99.5. We're asking for this. So the first thing we need to do is to check the condition. So the first thing we need to do is to check the condition. So in this example, the sample size is 20, which is less than 30, right? But we can assume that we can assume that the population is normal, which is usually the case, and it makes sense to do this assumption, so we can go on to use the formula listed in this table. So the second thing we can do is to find the sigma. Let me change sigma x bar, which is here sigma over square root of n, which is 20. Do this 1.2 square root of 20, which is 0.268. And the next thing is we want to find the probability. Actually, when we need to find the probability, it always comes back to the formula, which you are quite familiar with. Also in the, I think I mentioned it. I think that's covered in the my pre-recorded video. So this z-score, we are going to use the z-score to calculate, to find the probability. And since we are dealing with the sample and we are doing with sample distribution, so we need to make some changes. So z value of this 99.5 here, we'll change this to sigma x bar. So when you plug in the equation, plug in the number, so the z-score here would be 99.5 minus 100 over 0.268, which is 1.865. And since we want to find the probability, we just go and look up the z-table. Since we know the z value, we're going to find the area, or the probability of this z value. So it turns out that it should be 0.031. So this is the final value. So this is the first example. Oh, excuse me. The next example is about the proportion. So sampling distribution of proportion. So it says, suppose 15% of the 1,750 students at a school have experienced extreme level of stress, and during the first month, However, a newspaper doesn't know this figure and they are curious about it. So they decided to take a simple random sample of 160 students. And they find that 10% of the sample reply yes to this question. They said assume the true proportion is 15%. And what is the approximate probability that there are more than 10% of the sample? That is, so more than 10% of sample will experience the stress. So when you look at this, actually it's asking for this number. Just to remind you, you can always look up this website to see the see the explanation, detailed explanation. So here the problem saying that the proportion of this population is 15%. And now we have a sample of 160 students. And we find the proportion of this sample is 10%. So the first thing we do is check the normality condition to see whether it's satisfied or not. So we need to check whether NP is greater than 10 or N times 1 minus P is greater than 10. So NP is equal to 160 times 15%. And N times 1 minus P is N. It's 160 times 95%. And you can verify that they are both greater than 10. So that's good. So we can use the formula listed on the table. So the next step, we're going to calculate sigma p hat. According to the table, is going to be p times 1 minus p over n and take the square root of that, which is 0.15 times 0.85 over 160, which is, let's see, which is 1028. And then we can calculate the probability. So again, it turns back to the z-score calculation. So the z-score of this 10% is equals to p at minus p over this sigma p hat, which is 0.1%, 10% minus 0.15, 15% over 0.028, which is negative 0.05 divided by 0.028. So negative 1.79. And when you go and check the z table, I'm not going to demo this. You're going to do this and find the So look up the Z table. And we find it is around 0.04, if I'm correct. So another thing we need to look at is what the problem is asking. It's asking for the p-hat greater than 10%. And what we get here, this number, is actually the probability of p-hat is less than 1. So in order to get this, we need to 1 minus. So 1 minus p-hat less than 10% is equal to 1 minus 0.04, which is 0.96. So this is the answer. So that's all the thing about the sampling distribution. If you have any questions, please feel free to ask. So for the third part, after we finish the sampling distribution, we go to the estimation. And there are two things about estimation. One is the point estimation, which is pretty straightforward, which is saying that the population mean, which is mu, is equal to the sample mean. As you can see that this estimation is not that useful because as the sample varies, you will get a very different value of the population mean, and it's not that useful. So people think of what we can do to kind of estimate the population characteristic. So people invented this confidence interval, which is a range, an estimated range of a parameter. And basically, we just estimate the range of the population mean. So there's a table below, and I intentionally leave it empty. So I'm going to fill some part for you, and you're going to fill it by yourself for the other part. So it's similar to the table I showed you before. So for this part, it's going to be a categorical data, and this part is the quantitative data. And both condition and the spread is the same as the previous table. And the confidence interval here, I'm going to go over this. So the confidence interval is actually equals to x bar plus m minus m. So what is m? M is the margin of error. And m is equals to, I'm going to list out here. So m is going to be z critical times sigma over square root of n. Actually, I can rewrite this. Actually, this is Z critical times sigma X bar, or Z critical times sigma P hat. So I'm going to fill out this here. So if sigma is known, the formula would be X bar plus or minus Z critical times sigma over square root of n. If sigma is unknown, I'm going to approximate sigma by the sample standard deviation. It would be like this. And if P is known, oh, sorry, this bar should be here. I forgot that. So if P is known, so it would be P every P hat plus or minus Z critical times P 1 minus P square root of n. If P is unknown, if you replace the population proportion with the sample proportion, oh, sorry, n, and this should be also n. So when you look at this, it is nothing but the things in the sampling distribution. When you look at this here, and I say the condition and this formula are all the same. So you're going to fill it out by yourself. And this is the confidence interval of the parameter for, yeah. So these are all the formula, and you're going to see it when you do the hypothesis testing, because it's often that at the end of the hypothesis testing, you're going to be asked like the confidence interval of that. So the next main plot is the hypothesis testing. So I'm only going to cover the z-test today. So what is hypothesis testing and why do we use that? It's important to understand why. So the purpose of hypothesis testing is that we want to check whether a conjecture is true or not. To be more specific, it is trying to see the probability of a sample, which is usually a simple random sample, belongs to H0, belongs to the population, and H0 is the non-hypothesis. So if this probability is very low, which means your sample, your data falls in this edge of the distribution, which we are going to reject H0. if your probability falls into this part, we are going to fail to reject it. And that comes to the idea of type 1 and type 2 error. So this is actually kind of a tricky thing. So what is type 1? What is type 2 error? It's very likely that you may like get confused. Which one is the type 1? Which one is the type 2? So let's look at the table. So one important thing is to remember the top left, this top left corner, what should we put it here? It should be put H naught is something. And then on the left hand side, we're going to, one is reject H naught and fail to reject H naught. And for this part, we're going to say H naught is actually true or not. So it's true and false. So if H naught is true, the null hypothesis is true and we reject it, this is the type 1 error. Type 1 error. And the probability of the type 1 error, we use alpha to denote it. And the type 2 error is on the other corner, which is when the H naught is false, but you fail to reject it. So this is type 2 error. And we use beta to denote it. So actually, so all this probability actually is kind of a condition probability, but you actually don't need to know the detail of it. So, and this is also called the false positive. You may wonder, why is it positive? It's kind of weird. But when we look at our hypothesis testing, we have two hypotheses. One is the null hypothesis, another is the alternative hypothesis. So the hypothesis testing is based on the assumption that H naught is true until proven wrong, which is the case like a person is innocent until proven guilty. Until proven guilty. So when we reject H naught, which means it is positive. Reject H naught means actually the H1, the alternative hypothesis, is true. So this is positive, this is negative. for the whole row is positive and this is negative. And so the type 2 error is called what? It's called false. False negative. And if it is false, we reject it. So it's a true positive. This is a true negative. So if H0 is true, we reject it. So the probability is alpha. If it is H0 is true, but we fail to reject it, what's the probability of that? So it's kind of a complement. So it is 1 minus alpha. So the same thing is here. H0 is false. We fail to reject it. It is beta. So if we reject it, which has a probability of 1 minus beta. So that is the table of type 1 and type 2 error. And the next thing I'm going to go over some example, and like here is talking about whether you are going to use z-test or t-test. So there are a lot of kind of chart to tell you how to do that. You may want to follow that, but for me, all the things actually sum up to these two conditions. So when you try to find out which test you want to use, the first thing you want to check, as usual, when we do the sampling distribution, when we do the estimation, the first thing we need to do is also the same. Here, we check the normality condition. So if either of these conditions satisfies, we can say that, oh, this sample satisfy this normality condition, and we can go on and see and use all those nice property, the formula we discussed before. So this is the first thing we need to check. And the other is sigma is known or not. Or in the population, or in the proportion part, the categorical part is like the proportion of the population is known or not. So if it is known, if it's given in the problem, we are going to conduct a z-test. If it's not, I'm going to conduct a t-test. And another thing to remember is that whenever you conduct z-test, you're going to look up the z-table, z-score table. When you do the t-test, you're going to find the t-score table, which is absolutely different. They're different. Don't mess it up. If you conduct the z-test and you find a t-test table, it's not going to work. So when you look at the graph, and you can see that if this condition satisfied, which is the normality condition, and you can see if the population standard deviation sigma is known, I'm going to have a z-test. If not, I'm going to have a t-test. If it's known, we're going to have a z-test. If it's not known, we are going to have a t-test. So this is actually basically the criteria to decide which test you should use. So here are some steps to help you solve the problem of z-test. It's also the same, almost the same when we come to t-test. We just need to change this to t-test value, and it is what you should do to do the z-test. So let's look at the example here. As always, you can always check this website. The problem is extracted from there. So the problem say that a teacher claims the mean score of the students in his class is greater than 82 with a standard deviation of 20. So the first sentence tells us that, oh, we know the sigma is 20. And he claims it is greater than 22. What the teacher claims, what the researcher claims is always the alternative hypothesis. And the null hypothesis is always something equals something. So always is mu is equal to 82. So it's saying that it is greater than 82. So it comes to the alternative hypothesis. So mu is greater than 82. It is always the equal sign for the H0. So if the sample of 81 students was selected and they got a mean score of 90, check with this significance level. So which is saying that we got a sample and it's 81. We got an X bar of this sample is 90. And alpha we want to check is 0.05. So actually we finished the step 1. We have already set up this hypothesis. And then we go to find the Z critical. So what is Z critical? So the Z critical, when you look at the alternate hypothesis, we find out that we want to prove that it is greater than 82. This is the distribution of H0. This is mu equal to 82. We want to find this greater than 82. And the alpha is 0.05. So which means the probability of this area is 0.05. And we are going to check whether our sample falls in this region. If the sample falls in this region, we can reject the null hypothesis. So the 0.05, so alpha is 0.05. So z-score table which is 1.96. Let me double check it. It is 0.051. No, it's 1.65. 1.65 or 1.64. So this 1.64. If we calculate the z-test statistic, we use again the formula. So it's x bar minus mu over this sigma s bar, which is s bar minus mu over sigma over square root of n, which is 90 minus 82 divided by 20 over square root of 81. And this is equal to 3.6. So for the fourth step, I'm going to find the p-value of this z-test statistic. So again, we look at the z-score table. We find out that the 3.6. So 3.6 is actually very small. It is smaller than 0.002. So it's a very small value. So, and then we're going to compare. So we're going to check whether the so whether this probability, which is the p-value. So we're going to check whether the p-value is less than the alpha to check. So p-value is less than 0.002. So the p-value is less than 0.0002. Is it less than 0.05? Yes. Which means there is enough evidence to support the teacher's claim. So we fail. Oh no, we reject. We can successfully reject, which not. So we have enough evidence to support teacher's claims, support H1, which is the alternative hypothesis. So that's pretty much it of today.